All right. So now we're going to introduce a new tool called a phase diagram. Now you might have seen these before, but essentially what they are is they're a plot of the pressure versus temperature and showing the regions within this plot that are solid, liquid, or gas. All right? And these regions change based on the type of material that we're showing a phase diagram for. For us, what you kind of need to do is, this is something that's not terribly difficult. However, usually or often students will freeze up when they see this sort of thing and not know what to do. If you just kind of sit and look and realize that this is pressure and temperature, a typical phase diagram question will look like this, and they won't show you where the solid, liquid, and gas are. And you'll have to kind of identify where the solid and liquid and gas are being represented here. Okay? So what you can do is look at pressure and say this is high pressure. And look at temperature. This is, again, increasing temperature, high temperature down here. And let's think about a solid. What do you think, Fred? Will a solid be, or will a substance be a solid at higher pressures or at lower pressures?
Pressures. I don't know. What about temperatures? I know temperatures. Lower temperatures would be solid.
Okay, that's good. That's good. Lower temperatures would be solid. So you'd expect maybe this, something down in this area in terms of temperature, to be solid.
Yeah. But I guess it's going, you see, two regions.
That's right. So this could be solid or that could be solid, right? Now pressure, remember we were talking about, for example, the boiling point of water, right? If you go up to the top of the atmosphere, high in a mountain, right, or fly high in an airplane, how does that affect the boiling point?
Water will boil easier.
That's right. Because why?
Because there's lower pressure.
That's right. And what does that mean, lower pressure?
What do you mean, what does it mean?
Well, when we say lower pressure, it's easy to say, but what we need to recognize is that there are fewer molecules of, in this case, the atmosphere, nitrogen and oxygen, colliding with the surface of that water, so it's easier to jump off into the gaseous phase. And the same thing exists for the transition between a liquid to a solid. At higher pressures, materials will more likely be a solid as opposed to a liquid. All right? So low temperature regions, we said, are probably likely to be a solid, and then high pressure would increase the likelihood of that being a solid. So that is how we can kind of look at this phase diagram that's unlabeled and realize, okay, so that's solid, low pressures and low temperatures. Wouldn't it be a gas, right? Because at low temperatures, the intermolecular forces are going to be stronger, and so the material is going to be a liquid. So this is our liquid, and then that helps us realize that that is a gas, and we can double check that. High temperatures, all right, that is likely going to be a gas. And then, whoops, sorry, we got this wrong. High temperatures and low pressures, that's our gas. High temperatures, high pressures, that's our liquid. Okay? All right. So essentially what we did is we had the plot, pressure and temperature, and then we just sat there and thought about scenarios that would likely create a solid. We said low temperatures, high pressures, create a gas, high temperatures, low pressures. Now for gases, if you increase their pressure, right, then they will get closer together and collide more frequently, and then that intermolecular forces will hold them together, right? So that'll make a liquid. All right. So crossing these interfaces here, so this, if I go back and forth between these two, and again, that'll be a typical question. You'll draw something like this. Say, here's a phase diagram. What process is represented by that arrow? So you'll need to sit and kind of label everything and say, oh, that is a solid going to liquid. So that is melting going this way, solid going to liquid, liquid going to solid, fusion or solidification, right? Freezing. Okay, good. So phase diagrams. Now, these phase diagrams have what's called a triple point, a point at which all three can exist, a given pressure and a given temperature at which solid, liquid, and gas can exist. And gaseous solid water, gaseous water, and liquid water, for example, will exist up in, Alaska, where you have ice on the mountains and water in the lakes still, and then there's an amount of water vapor in the air, right? So there are temperatures and pressures where this sort of thing happens, okay? And it's called a triple point. Excellent, very good. So, what is the temperature and pressure at which all three phases exist simultaneously?
Boiling. That's the triple point.
That's right, triple point. Good. All right, so here's a phase diagram for water, and we're going to compare this phase diagram for water to this one of carbon dioxide. All right, so water, if you take solid water, ice, right?
Yeah.
At room temperature, put it at room temperature, that solid piece of water will gradually melt into liquid water. Not surprising. And that's what we would expect most solid materials, if they're going to melt at room temperature, you would expect them to go to their liquid form. However, with carbon dioxide here, what we find is that at room temperature, solid carbon dioxide, which is dry ice. Have you ever dealt with dry ice?
Yeah, for Halloween once we put it in some water and made some, it looked like a witch's brew or something like that.
That's right. That's dry ice. If you set dry ice on the ground, now this is again solid carbon dioxide, as the molecules of carbon dioxide, which are really cold, solid, right? They warm up and start moving, the intermolecular forces at room temperature are still not strong enough to hold the carbon dioxide molecules together. And so the result is a sublimation, where the solid goes directly to gas, okay? And, that's another thing that you sometimes see people do. They take some pellets of carbon dioxide, put them into a soda bottle, seal it up really quick, and then throw it in the lake or something like that. And as that solid sublimes to a gas, the gas takes up much more volume than the solid does, and the resulting pressure will burst the bottle and create a big explosion bubble. It's not really an explosion, it's a release of that pressure. Okay, so let's look at room temperature here. Pressures, here's pressures, 1 atmosphere of pressure right here, right? And if you look at room temperature, you'll be, here's 100 degrees Celsius, so about 20 degrees Celsius right here, right? So the occur right here, like this. So if you have a solid and you're at this temperature and the solid is transitioning here, you see that it's going to go from solid to gas. If we go back to our water, right, room temperature, it's going to be right about here this time, 1 atmosphere, right about here, you see the transition goes from a solid to a liquid. Okay, very good. Now, we have one last thing to talk about, and this is about solids in their crystalline form. Solids in their crystalline form. And I think it would probably be best if we talked about this in a different video. So that'll be enough for now. See you next time.